of QED Protocol, which specializes in blockchain tech and zkRollups. So imagine this world where you don't have to tell everything about yourself. You can preserve some level of privacy. This is the tech that this gentleman is working to help build. And for the first time ever, zkRollups have been created on a UTXO-based chain. So give it up for Carter. Thank you.
So yeah, today we're going to be talking about Cityrollup, and it's a trustless zkRollup for Dogecoin or other chains that are UTXO based. So let's get into it. First and foremost, just brief introduction of myself. So I come from the more traditional security community. My sort of claim to fame is I made the first worm for a game console. So like I get remote code execution on one game console, and then I can spread that remote code execution to anyone that encounters them. I built a lot of like gaming industry stuff, modding stuff. I also ran a proof of stake block producer for a long time, and I saw with my own eyes how bad it can get. And later, based on my experiences in that world, I sort of woke up to the corruption that I was seeing and joined the proof of work movement. And I'm founded QED for that purpose. So let's talk what does a trustless zkRollup mean? Because we need to be very clear about these things before we actually go into how it works. First of all, we want to be able to deposit funds from layer 1 to layer 2. And we want to make sure that no matter what, the deposit must be credited in layer 2 if I make the deposit on layer 1. So if I, let's say, send some funds to a specific address that is a deposit, we must be guaranteed that those funds get credited to the right person on layer 2. And then in addition, the other basic function that we want to have on a rollup is that I can send the native token from one person to another, and that the users must be required to sign those transactions. So we have the same sort of privacy and, of course, security constraints that we see on L1. And ideally, the number of transactions on the layer 2, so let's say we do 1 million transactions on the layer 2, it shouldn't affect how difficult it is to verify that proof or to verify the rollup on layer 1, right? Because we want to be able to scale these chains and the security they provide. So if it's going to scale linearly, right, then we might as well just do the transactions on layer 1. But if we can get something better, and in the case of Groth16, we get constant size, then it's much nicer to have this invariant as well. But and then finally, users must be able to withdraw their funds from layer 2 to layer 1, and no one should be able to stop that from occurring. So we need to make sure that people can't, censor a withdrawal back to layer 1. We need to make sure that someone can essentially have an account on layer 2, right, receive funds on layer 2, and then later withdraw to maybe their friend's address on layer 1. So you should be able to have this autonomous account that can interact with layer 1, receive funds, send, and still have all of the same security assurances that you get on layer 1. And just to boil that down, the main thing that we want to have in a trustless zkRollup is that the only way to steal user funds on layer 2 must be by breaking Dogecoin or the parent chain's own proof of work security, right? But how do we verify ZKP on Dogecoin? So there's lots of talk of these Taproot and other interesting ways of getting ZKP verification on Bitcoin, but on Dogecoin, we don't have Taproot or SegWit. So what do we have? We have P2SH, right? So the redeem script size, which is the size of the script that's hashed to get your P2SH address, that's maxed out at 520 bytes, right? For block size, we're looking at a meg, and Opcat is not going to help us, right? So we're not going to be able to do these weird covenant kind of stuff to make this work just because of these limitations. But maybe with a ZKP opcode, we can do it. So we propose op check Groth16 verify. And essentially, the way that it works is you put the verifier key and public inputs and the proof for a arbitrary zero-knowledge circuit into the stack. And then you have an opcode, which just verifies that proof. And one of the public inputs is the SIGHASH of the transaction, right? So that way, my ZKP can introspect everything about the inputs and outputs of the transaction, and we can build a recursive covenant with it. So it fits in a P2SH script without having to modify any script size limitations, which is nice, and it's all forkable. But yeah, so using that primitive, we've built Cityrollup, which lets users transfer funds to a current block on L2's P2SH address, and then we make a tree out of those different deposits that we receive on layer 2. And then users can claim the deposit by proving that they control the SECP 256K1 key that made the deposit in the first place. And we can do that with introspection. And then on layer 2, we can send transactions back and forth all we want with a ZK-friendly signature scheme. And then at the end of the day, when I want to withdraw, I can withdraw from layer 2 to any layer 1 address. I don't have to own it. And all of these are enforced by a recursive pay-to-script hash covenant. So the key thing here is if I deposit into that P2SH covenant, I'm guaranteed one of two things. Either that my deposit is later spent by the block, and in that case, my deposit must be added to the deposit tree with the correct public key, meaning that I can claim the funds on layer 2. Or my deposit that, my transaction that I send to the P2SH, it's not included or it's not picked up, and then within 10 blocks, if it's not spent, we have a return to sender branch in basically the way the ZK circuit works. So if you wait 10 blocks, show some proof of work, I can then return the funds from this P2SH script to whoever initially sent it, right? So it's either going to be recorded on the layer 2 as deposited, or you're going to be able to get it as a refund. So we've kept that main invariant there. And essentially, as I mentioned, one of the public inputs is controlled by the users. So usually we'll use that to represent the state of the blockchain, right? And then the other one is this thing called the SIGHASH. And I know there's plenty of people in the room who know what a SIGHASH is, but essentially you can think of it as kind of like the hash of an unfinished transaction, or a transaction missing a few things but with most of the core information. And it's actually what you sign when you use your wallet to sign a Bitcoin or a Dogecoin or a Litecoin transaction. And from this SIGHASH, we can know, okay, what are the inputs that we're spending? So one of these is going to be the previous block, right? So one block is going to spend to the next block. But then it can also include deposits from a bunch of users. And we can guarantee that within that zero-knowledge circuit, that any of those inputs that are being spent that come from people must be recorded as deposits. And in addition, we know what the next block script is going to be, right? That next P2SH address that we're going to be sending money to. And the way that we've created this recursive covenant is that the state root of the entire layer 2 chain is hard-coded in that 520-byte script, right? So I know what the next start state of the next block is going to be in the spend of the current block, which means that I can enforce a state transition from the current state of the layer 2 to the next state of the layer 2, right, using this covenant. And additionally, so over here we've got our block script, we can have other outputs too. And what are those? Your withdrawals, right? So I can constrain that the only other spends that are allowed to happen besides the next block script are withdrawals that were made by users, and we can constrain that they're going to the correct withdrawal addresses that the users specified on layer 2. And all this is enforced by the magic of proof of math, right? So it's not like we have to have a different consensus for this. We don't need proof of stake. We don't need any of it. All we need is a mathematical proof that when we're spending the current block, that P2SH address, we're spending all of the inputs to it, that the outputs that we're creating follow the rules set up by in the ZK circuit, which constrain the rollup to behave correctly, right? So the only way to break it is, of course, to break the proof of work of whatever chain we're building this recursive covenant on. But yeah, just to go into a little bit of technical nitty-gritty, this is like when I was saying, oh yeah, we're proving that the state root of the chain has been modified from its current root to a new one. What that means is, over here we have all of the users and their balances, right? So in a block, I'm proving that one user is transferring funds from another person, from one person to another, right? So these balances are getting updated. We're checking to make sure the public keys are correct. And we're also registering all the deposits and processing all the withdrawals. And if you're curious about this, the source code to Cityrollup is actually all open source, available on GitHub. You can start it up with a single Docker command. And again, what we're proving with each of these like covenant steps, so whenever I do a block spend on the layer 1 that verifies the proof, I'm proving that starting at some state root, I legally transition to a new state root as a result of signed user transactions that are updating these balances, and SIGHASH inputs and outputs which reflect additions made to the deposit tree, as well as things being removed from the withdrawal tree or withdrawals being processed, and those are reflected in the outputs of the covenant. So yeah, user key, very simple. I won't get too much into this nitty-gritty. Yeah, is this all just theoretical, right? Like from right now, I've kind of just showed you a lot of diagrams and charts and interesting things, but in fact, it actually works, and we've built a full chain RPC node wallet, the works, just to demonstrate that this is possible. So over here, you're seeing this live. Also, the proving is happening in the background, so you can see it's proving pretty fast. But yeah, so right now I'm claiming a deposit by signing with my, here we've got our Doge wallet, and here we've got the Cityrollup wallet. I can then transfer funds on L2 from one user to another. And then you can see over here, I can withdraw back to this layer 1 address. And then we can see that it's proving away. And if I go and I refresh my balance, I've got my 100 Doge that I've withdrawn. So we've already built this whole end-to-end, not only from a conceptual perspective, but we've written the code, built web wallets, everything. So if anyone believes that there's any trust assumptions or security issues that we haven't covered or that we got wrong, the code's all on GitHub, right? So come help us find any problems that you may have. But yeah, so it's not theoretical. It's ready to go. Hopefully, we'll deploy like a testnet so that people can access it publicly. Obviously, it's important that we do full security reviews on all of the additional code, specifically for verifying the ZKP. You may have noticed that our opcode is called op-check-graal16 verify that we are proposing, and we have Jens Groth, the namesake of Groth16, is helping us do that security audit. So he's like the honorary professor of, I believe it's UCL, who's going. He's a math genius. He's helping us do a theoretical analysis, and then we have some other security guys that'll be helping with code stuff. But yeah, another really cool thing about Cityrollup is that we prove the blocks in ov log n time. So we first generate witnesses for all of these proofs, right? And that's done serially. But then, once I have those witnesses generated, we have a network of provers that can go ahead and prove a tree of these proofs that consummate in that state transition proof there. And then once we've done that, we have to generate 3 separate proofs. So in this case, we have 3 separate like inputs, right? So we have to generate 3 separate proofs, 1 for each one. And then those proofs are included in the actual transaction, right? But whenever you see in this graph, like the proof sort of moving into another proof, what we're doing is we're taking a bunch of proofs and we're verifying them in another proof. So if I start off with like 1 proof for each transaction, if I start off by proving a ton of different proofs on a bunch of different machines, 1 for each transaction, I can then, after those are done, I can then group them into groups of 2 and then verify those 2 proofs in another proof. So the number of total proofs decreases by a factor of 2. And we can do that step by step, hence the O of log n, right, proving time, until we have a single succinct proof that has verified all of the other proofs that occurred in the block, right, all of the other transactions and events. So not only have we built a full end-to-end example of Cityrollup on our fork of Dogecoin, but we've also built it so that it's horizontally scalable, which is also nice, and has a distributed prover network. So to do the 2-to-1 proof recursions that I was mentioning, where you verify 2 proofs in one, along with associated like delta Merkle proofs, it takes like 200 milliseconds on a MacBook. For networking, we would imagine transmission, it's like a 100 kilobyte, or no, it's like a 60 kilobyte proof, so it fits in like a TCP packet. Let's say 100 milliseconds. So and the final Groth16 recursion takes 14 seconds. So if you had a ton of prover nodes, and you wanted to build a real Cityrollup, if you wanted to deploy it in production, and you had a ton of provers, The limiting factor would be around like 19 seconds for 100,000 transactions, right? Because as long as we can prove fully in parallel, and this is assuming essentially that you have 50,000 nodes, of course, but yeah, if you did, you could prove 100,000 transactions in 19 seconds. So it's scalable too. But yeah, so this is the architecture. Again, this was a proof of concept. We want this opcode, and we want ZKPs to be more integrated into the world of proof of work, because there is such a magical thing about ZKPs, which is that we can extend the security of the world's most secure applications, which are Bitcoin and Litecoin, to other applications without having to change the underlying super secure applications in the first place all that much, right? You add one ZKP opcode to Bitcoin and Litecoin and Dogecoin, hopefully, and then we're in a place where anyone who wants to make any VM or program that they want to verify on chain, they can, and the protocol itself won't need to update in order to support that. So yeah, this is just like the architecture. Basically, there's some caveats in the way that we've built it. Number one, the sequencer is still serially bound. QED fixes that, but yeah, like right now, the P2P, like the peering for our proof workers is like centralized, but you could replace that with a different P2P library. And the DA isn't decentralized and serially bound by design, and there's no smart contracts. But of course, our main product is not Cityrollup. Our main product is QED, right? So QED solves all this. We have shared global state like Ethereum. We support a lot of ZK VMs. We're proved end-to-end recursively with ZKP. So every block proof verifies the previous block proof as well as any transactions in the block. So you verify like the latest block. You've verified every single transaction from Genesis. We support a bunch of different programming languages. We let you prove your transactions locally. It's super cool. You should come to our website and check it out, or follow us on Twitter. But yeah, I won't talk anymore. I know I've blabbed for a while, so thank you. Please follow us on Twitter, QED Protocol. If you want to check out the source code for Cityrollup, it's on there. It's on GitHub. And of course, if anyone's interested in working at QED, please let us know. So thank you, everyone. Does anyone have any questions? I don't know how much time we have.
You've got time.
Do you have any questions?
There's a timer.
Yeah, so maybe you mentioned it. Who's responsible for spending the UTXO that represents?
That's a great question. So technically, anyone can. Technically, anyone can. But you may want to have an election for that to ensure that as many transactions are as included as possible. But the way that it's currently set up, anyone who can have, I believe it requires you to have at least one transaction in a block, but yes, anyone can spend it. So let's say my sequencer goes down and someone gets a copy of the data, like the whole state tree, they can go start up a new sequencer, just install it from GitHub and keep proving away. So the way it's currently set up, it's not upgradable, although again, you could build this into the logic of your ZK circuit. It's not upgradable, and it's fully permissionless. So this is one of the benefits of having a rather simple structure, where in this case, for Cityrollup, we're not implementing smart contracts. It was out of the scope of our experiment. It's just transfer, so it's relatively straightforward. But yeah, so right now, anyone. Yeah.
When you make a deposit on Cityrollup,
Yep.
You have to wait for the block verification?
You have to wait until the block is... So, OK, the way it works is I send my funds to a P2SH address, right? That P2SH address is a script which, as part of what the script does, and essentially the only thing it does, is verify zero-knowledge proof that starts from the current block state, right? So when I spend that P2SH, if as the inputs to that P2SH, one of them is going to be the previous block, right? I'm going to send from the current covenant to a new covenant. The other deposits that are made can be included as inputs for that spend that includes the block. And any of those inputs that are included must be added to the deposit tree of the chain. However, if my input, so I sent to this P2SH script, right? Let's say I sent it while the block is already being produced, right? So I kind of gotten too late, right? In that case, essentially what happens is I have to wait a couple blocks, and then one of the alternative proving paths for the ZKP allows me to return an input to sender, right? So if I sent from address X and I do a little bit of proof of work, I can then, one of the allowed ZKP spend paths is a SIGHASH, which sends the money back from where it came. So I'm not guaranteed that my funds will be deposited in the L2. I'm guaranteed that they will either be deposited in the L2 or I will be able to refund the money back to me and only to me within the next 2 blocks. Because on Bitcoin or Dogecoin or Litecoin or any of these chains, there's no way to guarantee that all inputs to a given script are spent without maybe doing a bit of proof of work. Although we could do that, right? This is an option where you could but then maybe you need to have a little bit of a delay, how many confirmations we want, right? But this is also doable, right? It's a little bit more tricky just because especially with Dogecoin, the way the proof of work works is not as easy as Bitcoin, where we just current difficulty, hash some blocks. Yeah, it is doable as well to ensure that more transactions or all of the ones that are included. Although you also run into situations where it's there's maximum transaction sizes, right? So we can't if there's too many deposits in one block, some of those people need to refund their money to themselves, which again, super fast, 300 milliseconds on a normal computer to do it. So it's not it's a big task to get your money out. But you could imagine a world where there's 100 transactions to a given address. How many inputs can we reasonably have on a Dogecoin P2SH spend? 200? Okay, so let's say there's 1,000 deposits, right? Some of those people are not going to get included in the current block, and they'll have to wait till the next block. But again, they never lose their money. No one can take their money from them because it only allows you to spend it back to the sender, right? So it's not like I can spend someone else's money to another address. You have to return to sender. So those are the only 2 ways to spend. But great question. Yeah. Any other questions? Because it would require about 1 gigabyte of block space. So this requires 400 bytes per block proof, and so it would cost an enormous amount of money. It would require multiple blocks, so the latency of your rollup would be extremely high, or the time to finality on the rollup is going to be so bad that no one is going to want to use the rollup. And the cost has to be amortized for each block amongst all these users. And the worst thing is, let's imagine a world where all of our proof of work chains, all of the transactions are just verifying blocks for layer 2s. And they are all raised a bunch of money from VCs, and they're using that money to crowd out the other transactions on Bitcoin. So if I want to send Bitcoin to my friend, I can't because someone's paid Slipstream a bunch of money to do an optimistic roll-up on Bitcoin, right? We don't want that to happen. That's not a good use of our time, and we don't want to make Bitcoin unusable to try to scale Bitcoin, right? This is not what we've signed up for. So if you're doing these covenants, which you can do, and I did a lot of research. I believe we were the first ones to implement multiplication on Bitcoin since Satoshi disabled the opcode back on Bitcoin Talk, which I know no one uses now, but we published it there. So I get that frame of reference, but this is just going to be really bad for Bitcoin if every block, because how many layer 2s are there? There are more layer 2s than can, and especially on Bitcoin, everyone is going to want to be verify their block in every Bitcoin block because it's a 10-minute block time, right? So it's going to crowd out everyone, right? If we do these opcap-based rollups, and I don't want to see Litecoin turn out like that. And we need Litecoin to not turn out that because we got merge mining transactions we got to include too, right? So you guys should add a ZKP opcode. Maybe just we hope you will. Maybe consider it. But yeah.
Well, thank you.
Thank you very much.
Honestly, thank you for bringing so much energy to a very technical talk. It was awesome.
Thank you very much. You're too kind.
Awesome.